Hi everyone. So this is the continuation of the last lecture on community detection, and we have seen in the last lecture several, metrics that we generally use as a very naive approach for community detection. We have also seen, the motivations behind community detection, different types of applications, and so on. So now we today we'll go into the actual algorithm, right, that we use for community detection. And in general, please remember, when we talk about the community detection, there are two ways to tackle this problem. One way is we take some metric, right? We design some metric, or we take some state-of-the-art metric and try to optimize the metric in order to detect the community, right? This purely comes from an optimization point of view, and we can use different types of optimization techniques, right? It can be a greedy optimization, it can be a a kind of extensive way of optimizing it, and so on. So this is more of an more of optimizing a certain metric, okay? And the second way is basically something called generative approach, where we basically we assume that there is some underlying underlying generative function, and using the generative function or generative method, basically generative process, we try to generate the network. Okay, so we assume that we have the set of nodes, but we do not know the connections of those connections among nodes, and we know that, okay, there is some generative process which is responsible for generating the edges. Okay, and through the generative process we connect nodes, right, through edges, and then we look at how these connections are similar to the connections that are originally there in the graph, and then we try to compare them, and while doing so we detect the community. Okay, so that is more of a generative point of view, and this is more of an optimization point of view, where we take a metric and try to optimize it. These are two different schools of thought. So today we'll discuss about the optimization method, where we take some metrics and try to optimize them. Next class we'll discuss some generative approaches for community detection. Okay, so the metric that we are discussing today is called modularity. So modularity metric was proposed by Mark Newman in 2003, 2002, during that time, in one of his seminal papers published in PNAS, I guess, if I'm not wrong. The idea behind modularity is that essentially, right? So the metric, this modularity metric, was proposed for quantifying the quality of a community structure. So let's assume that you have some algorithm to detect communities, right? Now the question is, how do you know the goodness of this community? Whether say you have algorithm A, and through algorithm A you detect a community structure from a network. You have algorithm B, and using B you detect another community structure. And how do you know that the community detected by A is better than community detected by B? So we need to have some metric by which we can quantify the goodness of a community. Okay, goodness of a community structure. Okay, this was the idea behind this, right? So we assume that we have a community structure, and we measure the goodness of the community structure. Later we will use modularity, right, for community detection. We'll discuss this how, right? So now, for the time being, let's assume that you have a community structure. You have a community structure, and you detect the goodness of the community structure, right? Now remember a quick terminology, disclaimer. When I say that community structure, I mean to say that there are set of communities. Set of communities form a community structure, right? And when I say community, meaning a single community, group of nodes. Okay, please remember this. Right. So, so what's the notion of modularity? The notion of modularity actually stems from the fact that in random network or random graph, I hope you remember what is random graph. We discussed in chapter 2 what is random graph. A random graph is basically a graph where nodes are connected randomly by chance. Okay, You flip a coin. If the outcome is head, for example, you connect two nodes, otherwise you do not. So there is no preference, there is no preferential attachment as such, or there is no homophily as such because of which nodes are connected in a random network. So the idea is that the idea behind modularity is that in a random network, since there is no homophily, there should not be any community structure. In random network, there should not be any community structure, right? Whereas if a network is formed in a natural manner, for example, through homophily or through say preferential attachment, for example, then there should be a community structure. Okay, and this is the idea. So if you look at the group of nodes which has already been detected as a community, okay, now what you do, you try to understand that, okay, if this set of nodes were connected randomly, okay, through random network process, what would have been the connection, what would have been the number of edges through these nodes, what would have been the number of edges among these nodes. Okay, so you know that given a network, this is one community which has been detected. You also know the number of connections within the community, right? Now you ask the question that what happened if we had taken the same set of nodes and connected them randomly through some random network process, and what would have been the number of edges among these nodes in the random network setting. Okay, so the more the difference between the number of edges in the real community versus the random network setting, the community that is formed in a random network, the more the difference, the better the community structure. Okay, so this is the idea. You have a network, you try to generate a random network, a random counterpart of this network, random configuration of this network, right? And you already know in the original network that these nodes form communities. This is one community, this is another community, this is another community, that you already know through an algorithm, right? So if you group these nodes in a same manner in the random network, right, what would have been the number of edges in each of these communities, right? You have community A, you know the number of edges within the community in the original network. You can measure the number of edges within that community in a random network, and you take the difference. And the more the difference, the higher the chance that this community is actually a community, or this group, real world group, is actually a community, because this group is now very far or very different from its random counterpart. But if the two structures, original community and the random community, if the two structures are same, that means that this community, real world community, has been formed randomly. That means this community is not a good community. Okay, so that's the idea. Now the question is, how do you create the random counterpart, random network, right? So we'll discuss this. All right. So now let's look at the formula, right? So Q is the modularity, right? This is 1 by 2m. What is m? M is the number of edges. Okay, you have VE. Okay, then summation of all node pairs ij, right? Aij minus di dj by 2m. This is within the summation delta ci comma cj. I will discuss all these notations, right? So m, we know m is the number of edges. What is aij? Aij is the I comma jth entry of the adjacency matrix. You have this adjacency matrix, and this is ith row, this is jth row, this is the entry, right? So in case of unweighted network, this can be either 1 or 0. This can be either 1 or 0. Either I and j are connected or not, right? Or what is di? Di is a degree of degree of node I. Similarly, dj, degree of node j. M is the number of edges. What is ci? Ci is the community ID of node I. Community ID of I, meaning which community node I belongs to. Similarly, Cj, right? And this is a delta function, right? And delta function, we all know that if delta I comma j is 1, if I equals to j, otherwise 0. That means if Ci and Cj are same, then it would produce 1, otherwise 0. So if Ci and Cj are same, that means if I and j belong to the same community, this function will return 1, then only this quantity, because this is multiplication, right? Then only this part will be considered. If this is 0, then this part would not be considered. Okay? Meaning we take all pairs of nodes. For those pairs where nodes belong to the same community, we take this part into consideration in the summation, otherwise not. Right? Now let's try to understand the meaning of this metric. Okay? So forget about 1 by 2m for the time being. I will discuss what is this. Okay? And also we understand what is this. So we only consider those pairs of nodes where for each pair, 2 nodes belong to the same community, otherwise not. So you also understand this part. Now let's understand this part. What is Aij? Aij is 1 or 0. It basically says how many connections are there between I and j in the original graph. In the original graph, how many connections are there between I and j? If it is undirected, if it is unweighted, then it would be 1 or 0. If it is weighted, this would be the number of edges present between or the weight of the edge between I and j. So this is the actual number of edges between 2 nodes. So we have 2 nodes, and we know that these 2 nodes belong to the same community. That's why we are considering this, because this part is 1. These 2 nodes belong to the same community in the real world, in the real graph, right? So we look at how many edges are there between these 2 nodes in the real graph. This is the real part. Now let's look at the random part. Okay, this quantity indicates that what is the expected number of edges between I and j in the random graph. So this is the original number of edges between I and j. This is the expected number of edges between I and j in the random graph. Now why this is so? Why the formula is di and dj? I'll discuss. Okay, but in general, you see the difference. Real part, random part. You take the difference. You take the sum for all pairs, and you basically do some normalization, and that's your Q. Higher the value of Q, higher the likelihood that the community structure is a good community structure. This is the idea. Okay. Now let's try to understand this random configuration part. Okay. So what I've said, that the expected number of edges between node I and j is in the random graph is di dot dj by 2m. Okay, I will show why it is. Okay, so this comes from something called configuration model. So configuration model is a very good old technique, but this was used here in the Newman's paper. So configuration model is nothing but a randomized realization of a particular network. Okay, what do you mean by this? And remember here, the random network is not formed arbitrarily. Okay, there is a design principle behind the random network. How it is designed? So we have this original graph G, okay, V comma E, and we have its corresponding random graph that we are generating through the configuration model. So note here is that the set of nodes is same in both the cases. That means if in the original graph there are 10 nodes, in G dash also there would be 10 nodes, but the set of edges would be same, but the number of edges would be same. Sorry, the set of edges would be different. Okay, the set of edges would be different. E not equals to E dash, but the number of edges should be same in both the networks, in the original network, and its random counterpart. Okay, now how do we generate E dash? We'll discuss now. Clear? So the number of edges should be same in the original graph and the random graph, but the set of edges would be different. Okay, how do you generate it? So let's assume that in the original graph, this is the original graph, this is G. Okay, in G dash, what we do, we take same set of nodes, right? And now we will not connect them. Okay, what we'll do, we'll not connect them. What we'll do, we will basically create something called half edges or spokes, right? So these are half edges. Why these are half edges? What I've done, look at it carefully. So for this node, okay, for example, for this node, I have cut these edges and I have cut each edge into two parts. Okay, so for example, this node and this node, there is an edge, right? I cut it in two parts. So for example, this is one part and this is another part. These edges are not, so therefore these are called half edges. Okay, similarly for these edges, right, I cut it, so this is one part and this is one part and this is another part. So through this, what property will be preserved? We preserve the degree of each node. We preserve the degree of each node. So here also we know that this node has degree 1, this has degree 2, this is 2, this is 2, and this is 3. Here also you see degree 1, degree 2, degree 2, degree 2, degree 3. So if the degree is preserved, then degree distribution will also be preserved. So the degree distribution that we'll have here, you'll have the same degree distribution here, right? But now we basically connect these half edges or spokes, right? How do we connect it? We take a half edge, right? Say this is one half edge that we take. We toss a coin. We choose randomly. Right? So we choose one of the remaining half edges randomly, right? Say for example, we take this edge, right? And by coin tossing, say for example, this edge will be chosen. So we connect these two edges, these two half edges. It may happen that you choose a half edge which is basically associated with the same node. It may happen. So a self loop may happen. A self loop may have been created, right? So you take a half edge, you randomly connect it with any of the remaining half edges, right? For example. So this is the random graph. This is a particular type of random graph. Degree distribution will be preserved. Number of edges will remain same, but the edges, actual edges, the set of edges are different. Clear? So this is the random graph, G dash. Now in this G dash, I will prove that the expected number of edges between two nodes I and j is di by dj di into dj by 2m. I'll show that. Okay. So let's assume that I hope you understood this part. I hope you understood how this configuration model, through configuration model, we create a random graph. Okay. So let's assume that there are two edges, there are two nodes, I and j. Okay. And degree of this node is di, degree of this node is dj. Okay. So what is the total number of so these half edges are also called stubs, spokes, right? Half edges. So stubs or half edges, right? So what's the total number of half edges? What's the total number of half edges in G dash? Right? Bolo, what's the total number of half edges? This is sum of all degree. Sum of all degree. Right? Which is 2m. Total number of half edges. Total number of half edges. Right? Because each edge contributes to two half edges, therefore 2m. Okay. So this is the total number of half edges. Right? Now let us consider each of, so I am interested in I and j. Okay. Remember, I has di number of half edges, j has dj number of half edges. Okay. Now let us consider each of the di number of each of the di half edges. And what I'm interested in? I'm interested in looking at the expected number of edges between I and j. Okay. So this is I. Okay. And we have this is I, and we have di number of half edges. And let's assume another quantity I, right? Let's assume one the quantity I, okay. This is j, right? I comma j. This is capital I. Okay, this is just a quantity. This is a I comma j, and too many i's. Right? Say b. Okay. What is this? B ranges from, B is 1 to ... di. So there are, so B is the index indicating each of these half edges. Right? This is B goes to 1, B goes to 2, B goes to 3, and this is B goes to di. Right? So this I, B, comma I comma j, this indicates that this is some sort of indicator variable. This is indicator variable, right? Which indicates, I mean, which would be 1 if bth stub is connected to one of the, or any one of the stubs of node j. Okay. So I'm looking at the connections between I and j. I take one stub, right? And the corresponding ith value would be 1 if this is connected to any one of the stubs of j. Otherwise 0. Right? So this I in this indicator variable is associated with each of these half edges, each of these stubs of node I. Clear? Clear?
Yes, yes.
Okay, so what is the probability? What is the probability that I, ij, b would be 1? What is the probability? So this is same as the expectation, I, j, b. What is it? So a particular half edge, a particular stub can be connected to how many number of stubs in the entire graph? What's the total possibility? 2m minus 1. There are 2m total number of stubs, and 1 is this stub. So this stub cannot be connected to itself, right? So there are 2m minus 1 possibilities, and among them, what's the possibility that this stub will be connected to one of these jth stubs?
DJ
It would
by
be
2m.
dj. This is dj. Okay, so this is the probability. So this is the probability that a particular stub of I is connected to any of the stubs of j. Okay, so then what's the total number of full edges? Total number of full edges, right? I'm indicating it as j, for example, jij, between I and j, right? This would be, so jij would be nothing but sum of I, sum of ib, right? ij, b equals to 1 to d di, right? So let's assume that you know all the I values, right, for each stub. So you know the I values of this and this, right? How many such I values are there? Di number of such I values are there, right? Some of them are 1, some of them are 0, right? So total number of edges, full edges between I and j would be number of ones, which is this one, right? So, but remember, we always do it in the expected form because this is a randomized version. In different realizations, you have different variations of the network. You always take the expectation. So the expectation of this one, expectation of jij is nothing but expectation of some b equals to 1 di ib ij, right? Which I can move the expectation inside the summation. b equals to 1 di expectation of expectation of I b ij, right? And what is the expectation of I b ij? Is already this one, right? This is sum of di b equals to di dj by 2m minus 1, right? So this part is independent of b, therefore this will come outside, and we just take the sum of ones. So this will be di times dj by 2m minus 1. Okay, so this is the expected number of edges between nodes I and j in the configuration model, right? Is di times dj by 2m minus 1. This is something that you wanted to prove. Now you say why this is 2m, this should be 2m minus 1. When m tends to infinity, 2m and 2m minus 1 doesn't make, I mean, they are same. So di times dj by 2m minus 1 is same as di times dj by 2m, right? I hope this is clear. I hope this is clear, right? So so this is modularity, right? So we understood this part. right? Now, why this 2 times m? Why 2 times m? Think about it. Why this is 2 times m? In the best case, this would be 0 and this would be 1. Okay, if this would be 0, this would be 1, then if you take the sum, if you take the sum of this difference, so the difference, so this would actually be 2m, right? The maximum value of this would be 2m. Therefore, we basically divide it by 2m just to make the range, you know, just to normalize it between a fixed range. Okay, this is just a normalization factor. Okay, so now this is modularity, and this is called node centric modularity. Why? Because we take every pair of nodes and we check the quantity, right? If you reformulate it, right, you can actually get a different formula, right? If you rearrange things here and there, you get a different formula, and that formula is with respect to the community. Because you remember, I started by saying that you have a community, you look at the internal edges within the community, and you look at the expected number of edges within the community. That was a community centric approach. You take a community and you look at the difference, right? But whatever I have mentioned, although indirectly it says that you basically take a pair of nodes which belong to the same community, but essentially we are considering a pair of nodes, right? So what I will do now, I will reformulate it, or you know, kind of rearrange it, right, to make a community centric definition of modularity, right? So what we have seen Q equals to 1 by 2m summation of ij aij minus di dj by 2m, right, delta ci comma cj. Okay, so let me write some quantities in a different manner. Okay, so delta function already mentioned, this is kind of a indicator function. If both of them are 1, both of the arguments are 1, then it is 1. Both of them are same, then it is 1, otherwise 0, right? So can I write this? And remember, this is for non-overlapping community, disjoint community, meaning a node can only belong to one community. I belongs to one community and G belongs to another, only one community. So can I write this in this way? Ci equals to Ci comma I and delta Cj comma I summation of all I. Now what does this I is 1 to mod of C. What is C? C is the number of communities. C is a set of, so mod C is the number of communities. Right? What does it mean? It means that you take each community one at a time. I equals to 1, I equals to 2, I equals to 3, dot 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 I equals to mod C, right? And then you check this delta CII, delta CJI, right? If Ci and Cj are same, meaning if I and J belong to the same community, right, there should be at least one I, or at most, because this is disjoint community, at least and at most one such I for which this would produce 1, this would also produce 1, right? If say I belongs to K and J also belongs to K, or say community ID 2, for example, right? So when I equals to 2, Ci comma 2 would be 1 and Cj comma 2 would be 1, then this entire quantity would be 1. And remember, this quantity, the maximum value would always be 1, because there is the minimum value would be 0 if the pair of nodes I and J do not belong to any common community, do not share any common community, then it would be 0. Otherwise, this would be 1. So this is same as this one. I hope it is clear, right? So what I'm doing here, I am rewriting this. Okay. So what I'm doing, so 2m right, let us denote this by C. Okay, small c is the index for community C. Okay, so right, equals to sum of, I'm moving this inside summation, right? And okay, I'll do it later. Just let me first rewrite it one more time. 1 by 2m summation of, okay, I comma j a ij minus ti dj by 2m, right? Summation of c equals to 1 by mod c delta. Too many notation mismatch. Just a minute. So let me, sorry about this. What I'm doing, instead of indicating nodes by I and J, I am indicating it by U and V. Okay. So so let me write in this way. Otherwise, too many notation mismatch will confuse. So this summation of VW. So let's assume that there are two nodes. Instead of IJ, I'm considering VW. Okay. And A VW minus dV dW by 2m, right? Summation of I, right? And I is number of communities. I want to mod C. Okay. Delta CV comma I delta CW comma I. Okay, right. So, and remember one thing, right? Okay, so what I will do, I will move this summation at the beginning, I equals to 1 to mod C, 1 by 2m summation of PW A PW delta, right? Delta CV I delta CW I, right? This is one part, minus 1 by 2m summation of VW dV dW by 2m delta CVI delta CW I. Okay, is it okay? Now let us keep this part same. I'm not changing anything. Let this part remain same, minus I'm now only changing this part. Okay, I'm now changing this part. 1 by 2m summation of what I'm doing, I'm keeping the components which are associated with V separate and components which are associated with W separate. So dV, V, dV, delta CV, I, right? This is one part. Okay. Okay. Oh, so yeah, this is okay. This is 1 and 1 by 2m sum of W dW delta CW. Okay. So what I've done, I have kept components which are connected with V in one part, components which are connected with W in another part. Okay. All right. Now look what happened. So summation of I equals to 1 to mod C, right? What is this quantity? Think about it. What is this quantity? What is this quantity? This is I, okay? Remember, this is I. This is I, not 1. It's I. Okay, what is this quantity? What is this quantity? So what it is saying? It is saying that you take a community I, right? And this would be 1 when V and W belong to that community I, right? So you are taking all pairs of nodes and you are considering only those pairs which belong to node I, which belong to community I, right? You are taking, so you have this I community and you are taking only those nodes which belong to I and their corresponding entries of the adjacency matrix. So this is the number of edges. This is the number of edges inside community I, because both V and W belong to the same community, right? Because this would be 1, this would be 1. V and W belong to the same community, and for those nodes, for those pairs of nodes, you are checking the adjacency matrix entries, right? So this is nothing but total number of edges inside node inside community I, right? And when we normalize this by 2m, what does it mean? It means that the normalized number of edges, the fraction of edges which are inside community I. So this is intra-community edges, fraction of intra-community edges. So this can be represented by EII. EII is a fraction of edges inside community I. Okay. Now let's look at this quantity minus. Let's look at this quantity. Okay. What is this? What is this quantity? What does it say? So this would be 1. This would be 1 when the node V belongs to I. So for all such nodes, which belong to I, you take their degree, you sum their degrees. For all such nodes which belong to I, you basically sum their degrees, right? Okay. And what is this? What is this? What is this? This is also same. You for all, because V also ranges from 1 to mod V. W also ranges from 1 to mod V. So this is also same. For all such nodes which belong to I, you take the sum of degree. Right? So basically this is nothing but something called AI square, because this is also, this is AI, this is also AI. What is AI? AI is the sum of degree of nodes in community I. This is also AI, this is also AI. Therefore, AI square. Now, this is the community-centric definition of modularity. From I equals to 1 to mod n, EII, which is the fraction of edges inside community I. And what is this? This is the square of sum of degree of nodes in community I. Now, I mentioned earlier that in a community, you take the actual number of edges within the community, which is EII. And what is AI1 square? And of course, this is normalized by 2m. Okay, remember, this is normalized. Okay, this is not the sum. This is normalized sum. Okay, normalized sum means for a particular community, you take the sum of degree of all the nodes and you normalize it by 2m, because 2m is the maximum sum value, right? And that is AI. So AI square. So in a random counterpart, the expected number of edges within the community is AI square. Okay, this is community centric definition. All right, so this is the community centric definition. Now let us go back to the slide. So I have discussed this one. Okay, and these are examples, right? If you see the examples, you will see this one. So what we have learned so far, we have learned that if you have a community structure, you can use modularity to check the goodness. And if the modularity value is higher for a particular community structure compared to other community structure, then you say that the first one is better community structure compared to the second one. Okay. So now how do we detect community structure using modularity? Now modularity is a community goodness metric. Now, how do you use modularity to detect community structure? So there are two algorithms that I will discuss. Both of them are very naive, but turns out to be very effective. So first one is called, the first algorithm that I will discuss is called fast greedy algorithm. This is proposed by Mark Newman himself in 2003. And the idea is basically very simple. It's a greedy algorithm again. What we do, we start with nodes. Okay, you see here, this is the network for which you want to detect the community structure. You start with all the nodes, forget about edges. Okay, and what you do, you assign each node to one community. So there are number of nodes equal to the number of communities. So each node belongs to its own community. As you see, this color indicates communities. So you see here, every node belongs to its own community. So there are 10 nodes, for example, there are 10 communities. Okay. What you do now, you add an edge. Okay. Now, how do you select an edge? There are many mechanisms. So let's assume that you select an edge, right? Now you add an edge, and when you add, say for example, now okay, so first you choose a node. Okay, let's assume that you choose node 1. Okay, so node 1, so this is node 1. Node 1 has this edge, this as an edge, this edge, right? Among these 3 edges, you choose one edge. So let's say you choose this edge. Okay, you choose which one is node 1? So this is so let's assume you choose this edge, right? So you choose this edge, and what you also do, you assign the neighbor, I mean the other part of the other node, other side of the node in the edge, right? You assign that node to one's community, right? So you start with one, right? You start with one, you add this edge, right? And what you do, you assume that this node 2 now belongs to the same community where the node 1 exists, right? Now you see here in this configuration, node 1 and node 2 both have same color, right? Okay, this is one setting. You could have added this edge. If you add this edge, then you assume that node 4 and node 1 belong to the same community, right? You could have added this edge, right? So then you assume node 1 and node 3 belong to the same community, right? So you have three possibilities, right? Among these three possibilities, for which the modularity value is maximum. So if this is the possibility, then what's your community structure now? You have this community and all the other nodes belong to the separate community. So you have some modularity here, right? Now in this case, there's a community and other nodes belong to different communities. So you have modularity value here. You also have a modularity value here. So you basically check for which setting the modularity value is maximum, right? Let's assume that for this setting, the modularity value is maximum. Okay. So what you do, you add this edge, you lock this edge, and you lock this community structure. You forget about this. So after this iteration, you have this setting, okay, where you know that one or two, this node and this node belong to the same community, other node belongs to a different community. Okay, then what you do in the next stage, you do the same thing. You add one edge. Now what you do, you add this edge, and check, and then you assign this node to the same community, blue community, you check the modularity. Or you add this edge, you assign them to the same community, check the modularity. Or you add this edge and check the modularity, right? Okay, so then you select the best one and you lock it, and you go on doing the same thing again and again until unless you see the modularity value increases or not. Okay, so one thing to note here is that in the subsequent timestamp or subsequent iterations, it is also important that the modularity value increases. Let's say in the previous iteration, this was your final configuration, and let's say the modularity value was 0.2. In the second stage, when you compare these three settings, you realized that for this setting, the modularity value is maximum. Say this is 0.4, right? So these values should be greater than equals to this value. Say for example, it may happen that in this setting, among these three one, this is better, but the modularity value is 0.1, but this is less than this one, right? So we will not, we just add this edge, but we will not change the community ID. We will not change the community ID of the new node. Okay, we keep on exploring this. So what's the idea? Idea is that at every consecutive iterations, the modularity value should be increased, and we stop when the modularity value doesn't increase. Cool. So this is the idea. So this is a very simple greedy algorithm which was proposed earlier, and it had a lot of drawbacks. So I'm not going to the drawbacks. Then in 2008, 2009, right? Another algorithm was proposed, and this is by far the algorithm which was used heavily as a baseline in all the papers, right? If you look at all the papers, even till now, till today, we are using Leuven as a baseline method for our algorithm. So this is called Leuven method, okay? BGCN method or Leuven method. Okay, so Leuven is again a modularity maximization algorithm, right? But the way it maximizes is different from the previous one. Okay, so Leuven it basically iterates over two steps. Okay, one is called one is called modularity maximization, other is called community aggregation. At every step, two things happen. One is modularity maximization, other is community aggregation. So one step is done. Next step, modularity maximization, community aggregation. So at every step, two sub steps are basically executed. Okay, so let's try to understand the algorithm. So this is the algorithm, for example. Okay, and let's assume that you start from a particular node, seed node, or the initial node. Let's say you start from node 8. Okay, and again here also you assign every node to individual community. So at the beginning, each node belongs to its own community. Okay, so you start with node 8. Let's assume that. Okay, and what you do now, so node 8 has say the, okay, so let's assume that you start from node 14. Okay, so you see that node 14 has neighbors 8, neighbor 9, neighbor 10. Okay, so you randomly choose a neighbor, and you assign that neighbor to the community of the original node, of the seed node. So let's assume that you choose this one and you group to these two nodes as the same community. Okay, similarly, separately you group these two communities together, two nodes together, and again separately you group these two nodes together. This part is still same as the previous one. You take a node, you look at its neighbors, you consider one neighbor, you group them, right, and you keep the other nodes as is, right, and then you check the modularity. Then you take another neighbor, group them, check the modularity. Another neighbor, group them, check the modularity, and you take the one for which the modularity value is maximum. So so assume that this is the group for which the modularity value is maximum. Now, what are the other possibilities? Now, when you add these two, when you group them, group these two nodes together, now what are the next possible candidate nodes that you can group, right? So the 14 has its own neighbors, 8 has its own neighbors. So now the set of candidate nodes that you can consider now is the union of 14's neighbors and 8's neighbors. Okay, so again you repeat the same thing. You repeat the same thing again and again, right? And here also remember, when we do this thing at every successive step, we see the modularity value should be increased. Otherwise, we will not consider that grouping. We will not consider that grouping. Okay, so we stop when we see that there is no grouping. So let's assume that when you start from 14, after certain steps, you see that all these nodes belong to the same community, but we can't exit, we can't move further. If we move further, the modularity value will decrease. So you stop here. So you mark all these nodes with red color. Next, you start from another node, say node 1. You do the same thing. You say, let's start from node 3. You do the same thing, and node 11, for example, do the same thing. Right? So now this is called modularity maximization, because you keep on doing this thing until we see that the modularity value is maximized. So we basically now each node belongs to a community now, right? In the community aggregation stage, what you do, you take one community, one group that you obtained earlier, and you collapse them, meaning that the community, a community that you obtained in the previous stage, that becomes a node in the collapsed graph. So this graph is called super network or collapsed network. In the collapsed network, a group which you obtained earlier is basically indicates a node here, right? So you see that earlier there was a red group, green group, this blue group, and this sky group. So now in this collapsed network, there are 4 nodes: red node, green node, blue and sky, or whatever. Yeah, right, blue and sky. 4 nodes. How do you connect them? Right. The self loop indicates the number of edges within the group. So if you see here, within this red group, there are, for example, 16 edges, right? The 16 edges. So the self loop indicates the intra-group edges, and the weight is the number of intra-group edges, right? Similarly for this and this. Now the inter-group edge is, you can easily check this one. Now between this and this group, there are 3 intergroup edges, for example. You see here 3. Okay. In the community aggregation stage, you collapse communities into nodes. You look at number of intra-group edges that constitutes your shape loop, and corresponding edges, number of inter-group edges that constitute your edges here, right? Okay, and this is your collapse graph. On the collapse graph, you again repeat the same process: modularity maximization, community aggregation. So each pass constitutes of 2 operations: modularity maximization, community aggregation. When you get the aggregated graph, you repeat the same thing. You keep on clubbing groups into super nodes, right? Collapse nodes. And you stop here when you see that the modularity value is not increasing further. Okay, this is the algorithm. So when you get it, the final version, say for example, the final version says that there are 2 nodes, and these 2 nodes can't be clubbed together. If you club it, modularity value will decrease. So you stop here. Now you can easily unfold this node, because you know that this node, say for example, this node is formed by clubbing these 2 nodes, right? Now these 2 nodes are formed by clubbing these these two communities. So you can unfold it, right? So you know that, okay, finally you know that this node, this super node, has these original nodes in the actual graph. Similarly, this super node has these nodes in the original graph, and these are 2 communities, for example. This is called Lubel method, and this is by far the, I mean, not by far, this is one of the first algorithms, one of the fast community detection method that was proposed, and the data structure that was used in the algorithm in the pseudo in the source code was very intelligently chosen, and therefore the accuracy was great. Okay, and so this is the last slide. So we have seen modularity maximization and 2 ways to optimize the modularity. What are the problems in modularity maximization? There are 2 limitations, right? One limitation is called resolution limit. So in modularity maximization, say for example in Leuven, right? What happened is that, forget about Leuven, if you think of a very exhaustive way of maximizing modularity, right? You will see that these algorithms, modularity maximization algorithms, suffer from resolution limit. What is resolution limit? Resolution limit is a limit on the size of the community. So if you think of a network like this, okay, a network like this, okay, network like this, okay, this is called ring of cliques. You see, these are cliques, and these cliques are connected by ring. Okay, this is called ring of cliques, right? If you run modularity, you see that after certain stage, meaning if the clique size is very small, say 2 or 3, 2 cliques will be clubbed together. That means the modularity maximization algorithms are not able to detect small size communities. It always merges small communities into large communities. Therefore, there is a limit on the size of the community. Okay, this is called resolution limit. The next problem is called degeneracy of solution. What does it mean? Degeneracy of solution basically says that let's assume that you want to maximize the modularity. It may happen that given a modularity value, say the modularity value is 0.8. Let's assume that. Let's assume that you can maximize, and you can't go beyond 0.8. 0.8 is the maximum modularity value that you can obtain for a particular network. You will see that for a particular modularity value, there can have multiple community settings, multiple community structures. Okay, what I'm saying is that if you say, for example, in this network, again hypothetical example, if you take this network, it may happen that when you group this and this, you have modularity value 0.8. When you group this and this, you have modularity value 0.8. Okay, so you have two different community structures with the same modularity value, and there is no knowledge that which one is better than other, because both of them have same modularity values. So this is called degeneracy of solution. There can be exponential number of community structures with a same modularity value, and that's the problem, because you don't have a unique solution. Okay, we will see that the other algorithms we'll discuss in the next lecture. The other algorithms try to get rid of the problem of resolution limit and degeneracy of solution. Okay, thank you.